One thing I want to talk about today is optimizing queries. Now, you've probably heard of an index, even if you've never written one yourself. If you've worked with relational databases, you've heard people bandy about the term or the expression, create an index, speed that up, create an index. And so you've had some exposure to that. There's other tactics we have at our fingertips to optimize queries, to make them more performant, to make them more successful. And when you get into a distributed system, a distributed SQL operation, where maybe the data is now spread across multiple time zones, different nodes, you're on different zones or regions, that kind of thing. We have to reach for every tool in the tool bag. And so we're going to talk about a special tactic that you can use. Before we get to that, I want to say howdy to my good buddy here, Felipe. How's it going?
Hey Greg, how you doing? Uh, doing good. Kind of eager to learn again from the master, Greg.
Oh, you're very gracious. And I want to say what we brought, is once again we brought the tablet for we can do for optimizing. If I can write at all, optimizing SQL. so so what I wanted to bring with me today to this thing is it's always to me, I don't know, I work better when I have sort of a hands-on example of something that we can do and optimize. And so I wanted to talk about, and we used this in a prior episode, but I want to demonstrate a situation and what this can lead to. And let's get that scribbly out here. Okay. I need a little bit thicker brush here. So what we talked about is, imagine there's this device sitting in your enterprise. It's a big giant piece of gear sitting in a rack somewhere, whether it's on prem, whether it's in somebody's cloud center, whatever. You've got this thing, and we're gonna put some colors on this thing, okay? And so the thing has a status, okay? The whole box says it's green, okay? It's green. Here we can, in fact, even light it up with cute cute stuff here. Okay. This device has got two cards in it, okay? You shell out 10 grand for some of these boxes, they'll have multiple cards in it with features, whatever. And those those cards have their own status on them, okay? Each each card has got its status, whether the card is functional or not, because you want to know if the card goes down, I need to pop out the card and put in a new one, or I need to contact my sales representative and have them drop ship me pronto a replacement card because maybe one of them's a backup to the other, something like that. And then, interestingly enough, these cards have ports. These ports are where things hook in, and let's just assume it's the same kind of card, so they both have the same, they both have 8 ports, okay? Well, guess what? Every port has got its own status. Let's zoom in here a little. This is right, this is my tool I used to do painting on, and it's also fun to demonstrate concepts too, okay? So essentially, it's got ports on it. Now, here's just to round it out. This big hulking box itself has got its own ports. So maybe it's got like 4 ports on it, okay? That each have their own status, okay? So here's our imaginary device that we're on the hook to monitor in some data center, okay? You've built the app that needs to watch this device, and depending on what these indicators do, you need to respond to it. For example, if the whole server goes red, well, that's one thing. There's one response that you do. There's one person you contact on that respect. Okay. Maybe you contact the system administrator and he needs to go kick the box, reboot it basically. Okay. But if this happens, if the second card goes red, the cards are active backups to each other, and that's a signal you need to call a sales representative and have them ship you a replacement card, or you've got a drawer sitting in the ops center that has the spares, so you need to go swap it out. Okay. It could be one of these ports goes bad. That may not be a signal that the device has got a problem. It may be a signal that that circuit feeding the device has a problem. So you need to pick up the phone and you need to call who's ever managing the other end of that line. Okay. So essentially, you need to do some processing when something goes bad, when you get an alarm. And the information that gets handed to you is you get an alarm. An alarm comes in, and let's just let's round it out and say this is server 157. Okay, you get an alarm on server 157, and you get this alarm. Well, get this alarm on port. Well, here port. What was it port 1, which happens to be on card 2. Okay, so this is your situation. Is we need to do what we call event correlation. I need to take this piece of information and I need to figure out where it is in the system. So what I'm going to do here is, okay, let's clear it out. So we've kind of presented, here's our problem. Now let's look at this. Let's look at the data. We have a set of data that in our system. We have a devices table. Let's in the pencil a little here. We have devices, and we can see server 157 sitting right here amongst all the rows of data, because what we do is we have the host name right here. Now let's keep this simple, okay? Let's imagine that host names are case sensitive, because there's actually a whole nother can of worms you have to deal with the fact that actually in real life host names are not case sensitive. You could have server 157, or you can have server 157, or you could have a combination. And these would all be the same thing in standard nomenclature. But let's just keep it simple and assume that we don't have to deal with that. Okay. So we have this devices. We have a table that captures all the devices, because essentially there's one row per device, per box that's in our system. And we have server 157, server 001, we have server, 999, whatever. This is our situation. And then what we're mapping, and this is what we were talking about the last time, a one-to-many relationship, is we have that card table with a card name. And that we have card 1, we have card 2. What I'm not showing here is there's a primary key associated with each card. So you can have the same card could be deployed. It's got a model number, but it can be given a name. So maybe there's a card in slot 1, there's a card in slot 2, on another device, slot 1, slot 2, yet another device, slot 1 and slot 2 for this particular card. Okay. So we have a designation for a given card. And what makes a given card unique is this relationship pointing back to the server. So you can have server 157 with card 1, and it's going to have a foreign key pointing back to the server, okay? Because it's going to be this card's linked with this one, but it's fair to say that server 999 is the same model, and it too is going to have a card 1, which is different than the first card 1. These are different. I'm running out of space. Okay. So let's clear this out a little bit here. And then the last part of our thing is we're gonna map out all of our ports. Okay. You can sit there and say you've got port 1, port 2, et cetera, et cetera. Now remember, we said some of these ports are actually directly on the device. And I showed in the previous drawing that port, there were 4 ports on the device itself. So there's definitely a one-to-many relationship between the device table and this port table, okay? So you could have port 1, 2, 3, and 4 that are directly on the device, all right? But I also demonstrated each card had a one-to-many relationship. Now it's getting a little messy here, so let's pull back and let's try to sit there and draw this a little bit cleaner. So you got devices. We have server 157. We have card, and we have port. We have a one to many. We have a one to many. And then we have another one to many here. And this is a classic ER diagram, or entity relationship diagram. Well, there's something that happens in a lot of places, a lot of different shops engage in something to capture this data. And it involves what I'm doing right here is I'm kind of trying to chart out the relationship. I started with a physical diagram that depicted a one box, multiple cards, multiple ports. Where was everything in relation to everything else? And we call this data analysis. Okay. And I'm trying to capture what I'm trying to find out what these relationships are. And I just did. And it only took me about 10 minutes to get a core understanding here. We're trying to map where's the one-to-one relationships, the one-to-many relationships, the many-to-many relationships. So I'm not going to necessarily delve into many-to-many relationships here, but the whole idea is I want to get the depiction of what's the cardinality between these things. Okay, what's the relationship between them? And it feeds into a concept known as normalization. Normalization. Okay. And normalization is sort of a concept where we're smoothing out the data. We're trying to not depict the same piece of data multiple times. Okay. And there's different levels of normalization. And you may have heard of some of them. Okay. You may have heard of something that's called third normal form. Okay. That's what that's the shorthand for it. 3NF, if you see that bandied about in Reddit discussion threads, what have you, third normal form is a sort of normalization. It's a way that data is smoothed out and optimized in a specific way. Okay. Now, it's kind of hard to imagine what third normal form is if you don't go back and look at what some of the earlier ones are. Okay. Uh, Now, I'm not going to go too deep on what the other forms, but I want to just share you with what at least what the first normal form is. The first normal form is a concept where maybe in your data set that you've gathered, you have, I've got this server, I've got the host name, but I've got this server has other attributes, okay? So in this row of data, I'll sit there and have, what kind of device it is. It's a router. Hmm. What else? What's its, maybe it's model 1001, that kind of thing. Like it's got a model number, who manufactured it, Acme, the company, a company that makes everything, the company for the Wile E. Coyote. Google that if you don't know what I'm talking about. Excuse me. uh, Company. What's the phone number for your customer sales rep? 800-234-5678. I hope that's not a real number. That kind of thing. I've got all these attributes and I've smashed them together with commas. Okay. So, in a sense, I've kind of serialized the data, I've stuffed them together. And this is something where I would say, in general, this is not even meeting the first normal form because the first normal form says every piece of data needs to be separate and distinct. Okay. And that's because the whole idea is it's hard to pull out and optimize data if it's all kind of thrown together in a hodgepodge. If you could imagine taking all the bits of data for server 157 and just dropping them into a bucket all together. No, sorry, what first normal form is suggesting we do is let's come up with a little bit better structure where we're going to have the host name. Let's capture the host name. Let's capture the type of the device in a separate column. So I said router. let's capture model number in a separate column. I said this was model number 1001. Let's capture well, how about manufacturer? Okay, I'll put manuf here. Acme. And then, customer sales rep, okay, 800, whatever. And this is the first step of data normalization, is to take each value and break it out into separate tangible items. So you can reach for the model column, you can reach for the manufacturer column, you can reach for the CSR column to fetch that kind of data. And this is the first step of data normalization. Now, I invite you, after the stream is over, when you get a chance, go look up the other types. Go look up second normal form. We're going to go into a little bit about what third normal form is, but there's higher ones than that, fourth, fifth, and I think I've heard of sixth normal form. Okay. But in essence, what we're doing with data normalization is, this isn't the whole thing, but the one of the things is, a big reason is, why are we doing this? And the reason why is because we're trying to avoid duplicates. We're trying to the direction we're optimizing. Whenever you optimize anything for any reason, there's always some metric you're trying to optimize for. And in data normalization, you're fundamentally trying to optimize for having no duplicate data. Each piece of semantic information is, what you're trying to do is store it one time in one place. Okay. So there's a sense of, we just talked about, okay, server 157, we said it's a router, it's model number 1001, it's made by Acme. But then the question arises, are there any other devices that are the same type? Are there any other devices that have this model number? Is there any other stuff in our enterprise made by the same company? If there is, then maybe that structure I just showed, where we were storing the Acme company and the 1001 in the same table as the devices, may not be a good idea. In fact, if we're going to do third normal form, the general recommendation is, let's put server 157 in this devices table, but let's create something called device types in another table. This one, we can say we're going to have, there's a router type 1001 made by Acme. Okay. And then maybe there's another type of router, model 2002, the upgrade. There could be other stuff, like there could be switches, whatever you can imagine. So the idea is, at a certain point, we can sit there and do a relationship between server 157 is this one of these devices, but server 999 may map onto the same device type. And so what we've done is we've deduplicated the data, the way we're representing it in the database. And this governs how we're going to write SQL operations. Okay. We need to now, if we're going to get the story, if we're going to create an ops dashboard for the management, for whoever's managing our ops center, whoever's watching these devices and getting them repaired when they go down, or when they have issues, and picking up the phone, they may need to see that server 157 is down, and they need to know it's a router. They need to know it's made by 1000, it's device 1001. That may tell them what tech manual to go look into to fix the problem. They probably need on the screen who the customer service representative is. Where does that data need to live? Is it possible, if we're going to focus on third normal form, that actually we need a different table for company, manufacturer, whatever? So we need to store, Acme, and we need that phone number. This is the company, this is the customer service rep. And so we need a relationship between this and this. We need to deduplicate the content and optimize in that aspect. So to get the whole picture to put on somebody's dashboard, I need to join server 157 with this row up here, and I need to find this information. And this is the kind of stuff. Oops, let's get a bigger eraser here. Let's just do this. That's a lot of content. Okay. This is the kind of stuff that leads us to write, select star from devices, join device type on devices D, DT, D dot, let's call it D type foreign key equals DT PK. Okay. So this is going to let us take the device type and map into that other table that had information on what kind of router it was. But we also need to join into the company table, company C on device type dot C foreign key equals C dot primary key. Okay. And so with that, we were able to model an idea. Let's show a concept. This is what we're monitoring. We're monitoring these devices. Let me write, or let me depict what does that represent. We have multiple devices, server 157, server 999, and we're trying to optimize and not have duplicate content stored in our database. We're trying to store each type of device one time. We're trying to store each manufacturer, each company that's manufacturing the devices one time in the database. And that leads us to how we're going to write these join statements to find the data, to put it on the screen, okay? And this is all the stuff that lets us then, assuming we did that, we can write our cool little dashboard, monitor app, where they can see at the top, maybe they have a little list, and they can see server 157. They can see a little icon that's showing its status. Oh, it's red. And they have a little button, whatever. They can click the button, and down here, it's going to depict all that extra information. Server 157. It's a router. And so it puts all the stuff. So they can click on the device. They can highlight it. They click on it. They get a detail. They click on a high level parent item, and they essentially get the child level details down here that tells them, okay, I can pick up the phone and call. This is the number I need to call. And so this is where we're taking the physical concept, we're mapping it through data analysis onto our tables. We're coming up with select statements, and then that select statement then has to serve this application, okay, where we can feed it the stuff. And so now we've kind of baked our use case, baked our scenario of what we're trying to do. So we know at this point, we know what the correct query is, or we figured out the correct query to navigate details. So we can we can tell the ops people, who do you need to call? Who are you going to call to go fix it? Okay. So now let's look at what's actually happening in the real world. Now, so far, we've been talking about server 157. Okay. We use that as sort of our guinea pig, our experiment for how to noodle out the relationships. But now we need to look at the bigger picture. How many devices are we monitoring? Well, maybe we're actually monitoring 8,000 different sites. Okay. Maybe each site has got 500 devices. Okay. Maybe on average, every device has 5 cards. Maybe every device and card has, on average, Well, we saw we had four. Let's just pick four ports. Fundamentally, for a rough order estimate, we need to multiply all that together. Okay. So I can sit there and say 8 times 5 equals 40. 40 times 5 is 200. 200 times 4 is 800. So I've got 800, and then I need 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That may mean we have on average 80 million different combinations, if you will, that we need to be watching. Okay. So what we're running into is it could be a potential combinatory explosion of what we're having to deal with. All right. So this is where we start running into situations of, okay, so what do you do, when you have, when the alarm comes in that server 157 port 4 is down? Well, you need to go back to that relationship. You need to join everything together. Okay. I'm going to start writing that operation because remember we had device, card, and port, one to many, one to many, one to many. Okay. Select star from device. And I'm going to put, back up, left outer join card on card.device fk equals device pk. Okay, that right there should give us every device, and optionally, because it's a left outer join, optionally every card that the thing is associated with, okay, that's related to. So it should give us all the cards, and in the case where it's going to give us one row for just the device itself, okay, and then it's going to give us a row for every card linked to that device, okay. But we're not done. We need to additionally left outer join. Now what we just did there is we just captured this relationship in the select operation, okay? In fact, here, okay, I'm trying to push this out of the way here. So what we did is we just captured, awesome there. Okay, we just captured this relationship, okay? Now let's go and do a left outer join on the port. There, let's left outer join port. In fact, I'm going to do this. This may make it a little easier to read. That just gave me an idea. Watch this. Okay. Okay, let's do left outer join. If I could spell correctly. Left outer join. Let's zoom in here a little so we can see this better. Okay, let's do this. Okay. Left outer join port. And I'm going to call this one P1. Okay, I'm going to join into the port table in one way. P1 on, here we go, card PK equals P1 dot card FK. Okay. So in other words, this is this relationship. This relationship here. I see. I realized I can use the color coding to add the select statements match it. Okay. So this is a one-to-many relationship. Essentially, the port table for this to work has an optional foreign key pointing back to the card table that may or may not be populated. Okay. It's an optional relationship. And that means if it's optional, I'm going to use a left outer join to join the port table to the card table. Okay. But I'm not done. There's more. Let's pick a shade of orange for our next one. Because over here, what are we missing? We need to map this third relationship of the device to the port. So we're going to go left outer join. I am having a hard time spelling the word join today. Join port P2 on device PK equals P2 device PK. Let me pull this out here a little. So earlier we joined the port table and it was to link card to port where there's an optional card foreign key. A port is going to be associated with, let's just say this in general, a port is either associated with a device or a card, but not both. It's what its immediate parent is. So that can either have a foreign key that's optionally pointing to the port to the card, and there's another column, another optional foreign key pointing to the device. And they're both optional because we don't know which one it is. It's going to be one of them, but that's the only way we can enforce. It's hard to enforce saying it has to be at least one of them. And what this captures is this relationship. So we've mapped all of them. And this essentially is the relationship we need to capture, okay? Let me tell you right now, left outer joins essentially give you more rows because it's going to map whatever's on the left-hand side of the join. In this case, the device is on the left-hand side. Let's get some blue here. Maybe this will be best depicted. Whenever you do a left outer join, like this left outer join here, it's whoever's before the join statement is what's on the left-hand side. In this case, above it. So in this case, the device is the left-hand side. So the device is required. When you say left outer join, it means the card is optional, okay? So we're going to find the device and optionally the card. However, if I go to this left outer join, again, who's on the left and who's on the right? Well, I can see that I'm joining port right here. That puts the port on the right-hand side. So port is optional. And if I look at the queries, I can see the card table. So it's telling me in this context, the card is what's on the left-hand side, okay? So the card's required, the port's optional. And then finally, the third left outer join is again to the port table. And that's why we have to go to it twice because we're looking on a different criteria. This tells us the device is what's on the left and the port value is what's on the right. And what happens when you have this relationship is you start finding this is fundamental. This relationship in our monitoring system that we're designing and building here, this is a fundamental relationship. Let's remove all this. This is the way this particular system works. You can't escape this, okay? Which means this construct is going to start appearing. It can appear, first of all, we already showed it, that it has to be on the screen. It has to be on the screen for the ops person to just navigate, just to get information. We need to see this. People need to be able to click either on the device, they need to be able to click on a card, they need to be able to click on a port, they need to get to the fingertip knowledge that resides behind this. So they need the company information. Now, additionally, there's additional joins we looked at. There's joins to get to the device type. There's joins to get to the company information, to get to the customer service rep phone number. But it's built on top of what we have right here, okay? It's built on top of all this. So this is candidate. You could say, let's just build a view that we could use, all right? And that's a common paradigm is all a view is it's a pre-baked select statement, okay? It's a pre-baked set of joins, if you will. But one of the things that anybody will tell you is do not join views to other stuff, okay? A view is a final result. So fundamentally, this doesn't really solve our problem of create a view, okay? What we're going to run into is that, remember what we just derived on this order of 80 million rows. You know, it's a rough estimate. It may be higher, it may be lower, but we're going to be dealing with 80 million rows of information. Now, what happens if you're trying to search the entire system for that? Well, the way this is written, we're fetching everything and we're not flanging down. So there should be some tantamount thing of, that's hard to read. How about a darker shade of green? Where host name, I should have brought water with me, equals server 157. Now that should slim it down quite a bit because that should help optimize the first join. So it should reduce the rows and stuff a lot. But another thing is we start having to put this join all over the place because first we need the thing to fetch the fingertip knowledge, but then we need the same relationship, the same putting stuff together for our correlation logic, the logic that's going to process, server 157 port 2 down. When we see that, I'm not scraping off the this thing because I feel like I spent time to get the colors so you could see all the joins. And so I'm gonna hover on it a few more times before I delete this, before I clear the panel off. Our processing logic that handles incoming alarm data and looks for problems to react to, it's going to need this same relationship to find stuff. And it's not hard to sit down and noodle out what are other things we're going to need. Are we going to need reports? Is a manager going to come to me and say, hey, we need a report. We need to know how many alarms we got last month at this location. We need to get in a report that shows how many alarms that we had for this type of device. Somebody said those 1001 routers throw too many errors and we need to junk the device in the whole enterprise. Could you write a report that could show me a breakdown by device type based on all the alarm data we have? And so again, you're going to need this relationship. This query thing is going to be needed. And so the question is this performant? If I'm looking for server 157, then this query is probably good enough because indexing, first of all, you're going to, like, for example, I can talk to Cockroach DB specifically. By default, we have a primary index, okay? And it's not hard. It's covered in our training how to build secondary indexes. What's something that you're all the time querying against? Well, okay. All right, I have squeezed that one. Let's clear it. It's not hard to imagine. It's not hard to imagine that we need to go create index on device dot hostname. Okay. That's pretty straightforward. That would create what's called a secondary index. A primary index is automatically created on the primary key. Okay. And you create a table, CockroachDB automatically creates a primary index. It's these indexes you have to create by hand through some analysis. And we can see all the time, we're probably going to be searching on hostname to look in that relationship. And so if you're looking for a single host name in the entire enterprise, it's not unreasonable to think that your actual, I said server 157. That's kind of crazy. It could be, site Alpha Bravo Charlie server 157 is maybe a more realistic host name that they're going to actually pick. So at a glance, somebody can say, I know where that's coming from. that's out at site Alpha Bravo Charlie. So that's one. Oh yeah, let's do the green here. That's a good host name right there. If I'm going to search on this host name, I want to take advantage of secondary indexes. And a lot of people understand how this works, okay? But what about that query I mentioned earlier? Like, how many 1001 routers alarmed last month? Is that a query you can visualize your manager walking in and asking you to write that? You may not have needed that query to get the system operational. You may not have needed that operation to launch a data center to scale from 20 sites to 8,000 sites. You may not have needed that. But something that happened was that over time, the program manager has been having to allocate more and more people every month to patching devices. And all his staff keep coming back and saying, we're spending 60% of our time patching these 1001 routers. They keep breaking down and causing havoc. And the manager's like, I want to get to the bottom of this. Do we need to ditch that device or not? Okay, Mr. Software Developer who understands the data set, this is a report I need you to generate right now. How are you going to write this query? You need that relationship that we just looked at. You need all those left adder joins. You need to also join into the other tables correctly. But I can easily see at the bottom of that where, we've got that relationship we talked about. It's all up here. Here, let's write it this way. Join device card port. But then let's say where device type equals 1001, and let's imagine you have to imagine there's a table with all the alarm data. Every alarm that happens gets stored to a table where event dot date equals, last month. Okay. Oop. Let's zoom in. Last month. And probably somewhere in here, it's going to be a select sum. Okay. You want some kind of sum count. Now that's almost to what what your program manager is looking for. Sorry, guy, gal, whatever. Um, they're wanting you to flange down and focus in on this 1001 device. And they want to know, the context is, let's look at last month. You can go Google how to go write that query to match the date column that you're storing. This is almost what they're looking for. What they're looking for is they want the sum, but this is what they're actually asking for. Group by device type model, where event dot date equals last month. What they want to know is they want the sum of alarms that happened last month, and they want you to break it down on a per model basis. And they want to see what are all the different devices that are alarming, and is that one significant? Is that one stand out? And this is why you have things like group buys. They show up in things like these data analysis reports, okay? And so you're wanting to find this kind of information. Can you visualize what it takes to look for this kind of information in the enterprise? This is basically a scan every row type situation, okay? You're needing to go and look for everything. And then this is what's called an analytical query, not a transactional based query. This is not based on parsing incoming alarm data. This is based on looking back in the past. Different databases respond differently. If you try to run this type of query kind of on any database that has 80 million combinations of devices, it starts to take time. So you need to think about what you're doing. Am I going to have to go to every range on every node to fetch this kind of thing? And there's actually a solution for it that's rooted in the thing we started with called data normalization. And it's where these situations rise up that maybe we need to denormalize the data or denormalize it in some strategic way. And what this means is there may be circumstances where doing all these joins, particularly left outer joins, that's correct. That's been optimized to minimize duplication, but it may be in the situation that you're facing that gets in your way. You're not concerned as much about I need to find a single row. That denormalization, or sorry, normalization makes it very easy to go find a single row of data, a single item that serves your needs. Okay. When you're doing this kind of analysis, a denormalized table is beneficial. What do I mean by that? Essentially, I can go back to that big old query we wrote earlier. Select, I'm, I'm going to write it in shorthand. Select from device, left outer join card, left outer join port, P1, left outer join port a second time, P2. And this whole thing is essentially a subselect. Insert into, let's call it the analysis table. Okay, we use it for analysis. If I can spell the word analysis, insert into analysis all that data. What is that going to look like? I'm basically taking the relationship that I mapped and I'm generating an intermediate result set. Okay. Yeah, let's just clear the. And what I'm going to have is I'm going to have a host name. I'm going to have that type. So here we had server 157, that 1001. Actually, this is, got this backwards. We have router, we have model, and then we have more. Okay, so there's going to be a row here for the server itself. The rest of the columns are going to be nulled out. Okay, but then I'm going to see in another row server 157, and this time I'm going to get the cards. So it's called a mux card. Okay, that's fun. Mux card, 987, and then card one. And then I'm going to see another mux card model 987, and it's card two. Okay. And suddenly what should be standing out is I'm basically going to have a one row for every permutation of this. This is going to be an 80 million row table. Okay. By estimate, this is a denormalized set of data. And what do we see? We see duplicate values here. Okay. We see duplicate values here. And it's gonna be like that. But the idea is now, if we're trying to do an aggregate search and look at this table, we don't need to go through all the intermediate joins. The content is all right here. Okay. So when somebody says do a count or do a group by, I can sit there and flange down on these types. Okay. The other thing is, and when you get into based on this analysis, I may need a denormalized table. If they're going to start asking for monthly queries on a periodic basis, maybe the manager says, let's write that report. That report really, maybe the first time you wrote it by hand, maybe it took an hour for the report to run. Okay. And you turned it in. The program manager said, fantastic. Let's keep that report. I want you to run that report again on the first day of every month against the previous month. And I want it on my desk at 9 a.m. Every time on the fly thing is created, it's not uncommon for the program manager to say, good, put it in production. So in a sense, we can denormalize and search faster because now to search this table, I don't need to do all those joins. Okay. I don't need to go through the effort to write that. I've kind of got a pre-baked version of it. Now, what this requires is, what about changes? what happens when what happens when you add a new device? This thing needs to update automatically. Somehow it needs to be updating. And that's where you have things like triggers. Or you could use in Cockroach DB, you could probably craft a change data, a CDC thing. Whatever it is, you need to be having it. Now, ideally, hopefully, your device stuff isn't changing minute by minute, second by second. It may be this week we turned on a new site. 3 months from now, we activated another site. Rebuild the data, rebuild the table. And in this sense, we can start building indexes on that denormalized data set. And we can optimize the indexes and that denormalized table to serve the reports that we need to write. And the trade-off in that is it's okay. We're deciding that it's okay to have duplicate data in that sense because it makes the report run faster. Okay. I'm not having to run out to all the nodes, all the ranges to do a very complicated join operation. Instead, I can filter down, and it may be depending on how we structure the data and how we do the indexes that it's like, well, we can optimize that so that a given month's data ends up in the same range. And I end up, okay, I'm looking for that month's data. So I'm going to go to one range, or maybe it overlaps into two, and I don't end up having to go to everywhere because I was able to use denormalized data. Denormalized data to serve my needs. Now, what are the trade-offs? Because everything is a trade-off. Okay. Can you imagine what the trade-offs are? Put them in the comments before I give it away. But what are the trade-offs to doing this? Well, first of all, space. Okay, it's going to obviously require more disk space to have a table like this. Okay, here it is. If I'm going to have essentially fundamentally two copies of that data sitting in the database and being maintained, it's going to, it could easily 2x the storage space for that table, not for the whole database. Let's take the 2x out. I'm going to need more space to host this. What if your manager comes to you and says, "I need this other report. That report was really good. It had me thinking, could we get a 12-month report?" I don't know. Does the 12-month report work off that one? Maybe it does. Maybe it's fine. Maybe another secondary index that serves that report works better. But you may need, this is what I call being the victim of your own success. They may say, "Hey, you did that for that. There's this other part of the system. I would like to look into what happened last month." And you may need to build, you know, another denormalized set of data. So again, more space, more design, you need to make sure you're putting the maintenance in there that's going to maintain that the denormalized set is following the original set. And then you have to figure out, what am I going to do am I going to enforce foreign key requirements? Is the denormalized set going to demand? It may not be able to. Okay. Um, Foreign key or integrity constraints tax the system, and sometimes they're not. They're sort of a on or off thing. So if you have an optional column, it's hard to put a foreign key constraint on that kind of thing. Okay. So you have to check all that, check all the stuff. So there's a certain level of maintenance that comes with that, but it may be worth it. And this is the kind of analysis that you do. This is the kind of thing I can't tell you whether or not that fits your solution or not. That's the kind of analysis you have to do on your own data set, or talk to professional services. So this is the kind of thing where your own data may dictate your solution. And it's not, a I don't know, go build an index. Just go build an index. That's the fix to everything, is go build an index. And it's kind of like, not everything is just building an index. Sometimes you have to put this kind of thought and care and consideration in, and then build the index that supports that. So what you think, Felipe? You're on mute. Yeah, let me. Oh, I don't know if it's off. I don't know if your mic's off, but Mike fell asleep, but
Okay, can you hear me?
yeah,
Yeah,
yeah.
it
Now I
was.
can hear you.
I don't know. It was kind of weird. Let me add this and let me see or let us know if this is a right assumption. So I have these kind of a what you talk about on I was writing this down. Kind of the core objectives of normalization are uh, the first one. Normalization eliminates redundant data storage, right?
Exactly.
The second one, another thing that I was taking note, ensure logical data dependencies within tables, right? And the third one, so mitigate data anomalies like the update, insert, delete anomalies, right?
Yep.
Caused by redundancy. Uh,
Exactly. Yeah, that's a good one.
so yeah, very interesting, and that was a very cool way for you to show the different parts on with coloring. So that's something that
Yeah,
we should apply. The
need
next
to
time
remember that one.
we talked about and we start kind of explaining on the board different colors, that will help a lot.
So, and and that's where it's and what's kind of weird is if you don't know what data normalization is, I've worked with people that are they're fully vetted in it, they understand it, and they actually use it without thinking about it. And it was a concept I wasn't aware that the database we were building the system on that I'm borrowing this example from was a normalized data set. It was when the database administrator or DBA that was assigned to our software team to help us write select statements. He said, this query, we're not, he helped us optimize as much as possible. Then he said, we're not getting any further with it. I'm going to denormalize the data. And I said, what the heck is that? And then he explained it to me, and then it was like, you know. So then I got the point, and I was like, I was fascinated by that. And then he showed me what he did to ensure that the data was being maintained consistently. And he actually went through a few iterations because he built at the time he used something called a materialized view to represent that denormalized data. Um, a denormalized view, or sorry, a materialized view is essentially it's like a select statement, but snapshotted. So there was like real data, but it was captured in a select statement. But we caught the thing when it would regenerate it. It would use about a 20 millisecond window to regenerate it. And we would go we had enough selects hitting that view that more than once we hit the view and it was empty because we hit it in the 20 millisecond window. And we went and
Nice.
told him, and he said, okay, forget the materialized views. And then he just brute force wrote that insert like I did, where he joined all the data, stuffed it into a table, and then he wrote triggers, whatever, so that when these other tables would get updates or deletions, what have you, it went and updated that table. And I did not envy his job. But what I found out when we migrated to this paradigm, suddenly there were several critical operations that I could stop using that complicated join operation. And instead, I went to that table that had the denormalized data, and I started from there, and then I could join in the other stuff that I needed. And that was a lot faster. It was a lot easier to optimize, and I could go back and say, I need this, I need an index for this, and I need an index for that. And I could sit there and crank out reports all day for management. And then I realized, oh, okay, now I get it. This is the benefit. And so we don't denormalize everything because you could denormalize everything, but it takes us back to the stuff you just put in the bullet points. So, all right.
If you're enjoying the show about the database you just can't kill, then give it a big thumbs up and share it with a friend right now.
All right, everybody. We'll see you next time on Select Star.
This episode is over, but your learning has just begun. Visit cockroachlabs.com to find all kinds of content to expand your knowledge.